Welcome everyone. Let's get started on one of the most critical performance optimization techniques in Apache Spark. Today, we are mastering shared variables, broadcast variables, and accumulators. Let's kick things off by understanding how Apache Spark handles variables across a cluster. When you submit a Spark job, the driver program breaks your code into tasks and ships them to executor nodes. By default, any standard variable you use inside your transformations is copied and sent along with every single task. Imagine having a massive lookup table and 10,000 tasks. Spark would send 10,000 copies of that table over the network. Furthermore, if an executor updates this variable, the change is purely local. The driver node never sees it. To solve these massive network bottlenecks and synchronization issues, Spark offers two powerful tools: broadcast variables for distributed reading and accumulators for distributed writing. Let's explore how they revolutionize distributed processing. Take a look at this diagram. In a standard operation, the driver node sends a separate, identical copy of your variable to every single task on the executors. This is highly inefficient. It hogs network bandwidth and wastes executor memory, highlighting exactly why we need a better shared variable strategy. Now let's deep dive into broadcast variables. Think of a broadcast variable as a read-only cache distributed to every worker node. Instead of sending a variable with every task, Spark sends it exactly once to each physical machine. Every task running on that machine simply references the local cached copy. Why is this a game changer? It drastically reduces your serialization overhead and network traffic. When you have a large lookup table or a machine learning model that needs to be referenced by every row in your massive dataset, broadcasting it is the most efficient method. Under the hood, Spark utilizes highly efficient peer-to-peer broadcast algorithms to get that data out to the cluster quickly. However, be mindful of your memory. Broadcasting datasets larger than 1 GB can cause out-of-memory errors on your driver. Notice the difference here. The driver node broadcasts the data exactly once to worker node 1 and worker node 2. Then, tasks 1 through 4 simply read the data from their local worker's memory. This cuts down data transfer by orders of magnitude. Let's put this into a real-world perspective. Imagine you are processing billions of e-commerce transactions. Your transaction data contains short country codes like IND or USA, and you need to map these to full country names for a BI dashboard. You could do a standard SQL join between your massive transaction table and your country table. But a standard join triggers a shuffle massive movement of data across the network, which is the most expensive operation in Spark. Instead, we use a broadcast variable. You take your small Python dictionary of 200 countries and call spark.sparkcontext.broadcast. You then use a simple map function where you access the dictionary using .value. You have just successfully performed a map-side join, entirely avoiding the network shuffle and accelerating your job exponentially. In this flow, our small dictionary is wrapped into a broadcast variable. As our billion-row RDD flows through the map operation, it queries the local broadcast value. The result is an enriched RDD, achieved entirely without a network shuffle. Moving on to our second shared variable, accumulators. Have you ever tried to define a simple counter variable in your Spark script, increment it inside a map or for each function, and found that the final count at the driver was still 0? That happens because the worker nodes are updating their own local copies, not the original variable on the driver. Accumulators solve this exact problem. They are write-only variables for your executors. Because the operations are associative and commutative like addition, Spark can safely aggregate these updates from hundreds of distributed tasks back to the driver. Executors can add to it, but they cannot read it. Only the driver node has the privilege to call .value and read the final aggregated tally. They're an elegant solution for implementing global counters. This upward flow beautifully illustrates accumulators. Executors 1, 2, and 3 process their data chunks and push incremental additions to the accumulator. Finally, the driver node pulls the consolidated total of 10. Workers write, the driver reads. Let's look at the mechanics of working with accumulators. To initialize one, you simply call sc.accumulator, 0, on your driver. Next, inside your distributed operation, let's say a lambda function applied to your dataset, you define the accumulator as a global variable and call .add 1 or plus equals 1 whenever your condition is met. Finally, once your Spark action is fully completed, you call .value on the driver to retrieve the final integer. However, there is a crucial deep dive caveat you must know as a senior engineer. Spark guarantees exactly once updates for accumulators only inside actions like for each. If you update an accumulator inside a transformation like map and a node fails, causing Spark to recompute that partition, your accumulator will be artificially inflated by double counting. Always be strategic about where you place them. Our sequence diagram maps the exact life cycle. The driver initializes the accumulator, ships the task. The executor evaluates conditions and adds to the count. Upon completion, partial sums merge at the driver, which reads the final value. For our real-world accumulator use case, imagine you are a data engineer tasked with processing a 10 terabyte server log file. Your primary goal is to extract user data for analytics. However, the operations team also wants to know exactly how many corrupted records or warning lines exist in that massive file. You could write two separate Spark queries, one to filter and process the good data, and a second to filter and count the warnings. But reading 10 terabytes of data twice is a massive waste of cluster compute and money. Instead, you declare a warning accumulator. In a single pass over your data, you parse the good records, and whenever your code hits a warning, it simply increments the accumulator. One pass of the data, two business requirements fulfilled flawlessly. Observe the dual action pipeline here. As rows stream from the 10 terabytes file, valid data flows seamlessly into our clean data frame for storage. Simultaneously, bad rows increment our accumulator, allowing us to generate metrics without slowing down the primary ETL. To ensure absolute conceptual clarity, let's put broadcast variables and accumulators head to side. They solve two different sides of the distributed computing coin. The direction of data flow is reversed. Broadcast variables push data out from the driver to the executors. Accumulators pull data in from the executors back to the driver. Regarding immutability, broadcast variables are strictly read-only for worker nodes. They cannot be changed once broadcasted. Conversely, accumulators are essentially write-only for the workers. They can add to the value, but they cannot read the current sum. Use broadcast variables to eliminate shuffling when joining large and small datasets. You use accumulators when you need global metrics, counters, and telemetry without forcing a costly network reduction. They're your two best friends for advanced Spark optimization. This side-by-side comparison makes it crystal clear. On the left, the heavy arrows push read-only data down to the executors via broadcast. On the right, executors push their write-only tallies up to the driver via the accumulator. Let's summarize with some critical best practices from the trenches. First, respect memory limits. Only broadcast tables that easily fit into memory, typically under 200 megabytes. Spark has a hard limit of 8 gigabytes, but doing that will likely crash your driver. When you are done with a broadcast variable, call .unpersist to free up cluster resources. Second, for absolute accuracy, update your accumulators inside Spark actions, not transformations, to avoid double counting during task retries. By mastering broadcast variables and accumulators, you eliminate expensive shuffles, prevent out-of-memory errors, and write enterprise-grade, highly optimized Spark applications. Thank you for joining this deep dive. Please like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you in the next session. Our final diagram is your optimization checklist. Always verify your broadcast sizes, ensure accumulators run inside actions, and unpersist variables to free memory. Follow these steps, and you will undoubtedly master Apache Spark performance tuning.